All right, so yesterday we started the problem. I don't have it with me. I just have the continuation of the fuselage frames, no? Okay, and we did the load on the top flange and the lower flange. On the top flange, I think everything was in tension, but on the one at the bottom was compression, but because of the extra 2 stiffeners we added, no? It created a change on the deformation, and then it was going from compression to tension on the last segment. Okay, you should have it on your class because I did not bring it. So I decided, Johnny, I was telling you that maybe I was not going to do it, but I don't want to give you the bad impression not to leave problems fully complete. So let's complete the whole problem, okay? All right, so let's do today the stiffener. DKH. Okay, so that's the stiffener. That's always the same procedure. So I think that's the one that is cut over here where the load is applied. Of 4,000, where this is 60. And if you remember, what was the load at the free end of the cantilever frame or the cantilever beam, if you want? We say it was 0, no? Okay. All right, so on this side, we are here Q1. And on this side, Q2, even though I think Q2 was going down. Or was it going up? I don't remember. Was it going up? Q2 was positive? Okay.
Q2 value was negative is what we found, but when we did the initial assessment, we had Q2 going.
Okay. Okay. So whatever it is, it is. Okay. So basically what we're going to do is follow the same procedure. Okay, but let's say over here. So now let's say recalling. From solids. A cut must be made every time there is a discontinuity in the load. So really this is not only solid mechanics, but also static, no? Remember when you had to find the shear and bending moments diagrams? You need to do a cut every time this is discontinuity. So if we start from this end, the load at this end is 0 at point D. Then over here is going to be the same. Then what's happened at point K? There's a force applied, so it will be discontinuity, no? Okay, so you need to make a cut somewhere between D and K. So let's make a cut somewhere over here. Okay, so let's say cut. I mean, it can be anywhere. Let's just put it here, just somewhere between D and K. All right, so let's say here, let me just say first cut is only one, but let's just call it first cut. So what do we need to do? We start from point D over here. We know F of D is equal to 0. We start over here the deformation. Let's say this will be S. I want to call it S. Then we make the cut over here. So you will have only Q1 over here. And what I'm trying to look is not the moment, but just the axial force, no? The force in the member. So let's call this one over here. I'm uploading in tension. Let's say it would be F dk. If you have any question about what we're doing, stop me, okay? So over here, if I do summation of forces equal to 0 on the direction of the element, what are you going to get? F dk would be positive minus Q1. That would be moving what distance? S, no? Yeah. Equal to 0. So this is going to give you that F dk would be equal to Q1 times S. And I mean, I don't have here the data, but I think I don't have the class note, but from what I have over here, I guess Q1 was equal to 11.3. So this would be 11.3 S. Okay, so basically what would be the variation? At FD would be 0, and it will be linear increase, no, up to point K. And what would be the value at point K? So it would be F of, let's say F of K would be equal to what? Be equal to F of dk at what location? That distance over here was how much?
200.
200, no? Okay, so it would be 200, and that gives me that this would be equal to 2,257.1 newtons. Okay, and again, I already put FDK equals 0 at 0, no? Okay, so we made the cut. Now what do we need? Now we need to see what happens once you pass the cut. So we do another type of the same figure. Let me do a little bit longer. So we have 2. Let me do 3 over here. Here we still have F of D equal to 0. Maybe let's cut this one second cut, and I put it over there. So second cut, pass the discontinuity. So let's say first cut will be this one. Second cut. So what do we have over here? This will be point K. Again, we're gonna have S over here. This will be Q1. This will be Q2. And this will be F KH. And I have over here, I don't know, I mean, again, I'm just copying here. I don't have the notes from yesterday, but I have here that Q1, we found 11.3 and Q2 to 2.57.
You can slide it up a bit.
Oh, yes, so, yes.
Maybe.
Yeah. Okay, I'm forgetting something here. We're forgetting what? Let's not forget that why we had to make the cut is because there's a force over here of F1 equal to 4,000 at 60 degrees, no? So if we apply the forces along the member, all right, what are we gonna get? So again, that distance over here was how much? $200. So what are we gonna get? Okay, let's do F. Let's start the same before FKH minus, what can I say? 200 Q sub 1, no? Now put 200 because we already passed we make the whole 200, no? Yeah. Now, what about Q2? Q2 starts at point K. So what would be the distance of point Q? How much would that be moving? What would be that distance here from here? So it will be S, no? All this S minus this section here, no? So it will be Q2 of S minus 200. Any question? Now we need to look at what is the component of the force 4,000 acting along the member. So what will be that force? Will be 4,000 what? Cosine or sine?
Cosine 60.
Correct. Cosine 60. And this will be equal to 0. So now if we solve that equation, we do a bit of algebra, we get FKH. This gives you will be equal to minus 2.5709 times S plus 771.28. Yeah. See what happened yesterday? Can I make it a bit smaller? No, that's all I can. Okay.
Professor,
Yeah.
could you repeat why is that b equal to 0?
Why this is equal to 0?
FD. Before that.
Okay, because FD, I don't have the figure, but FD was, if you look, would be the member that was at the end of the cantilever beam. So in other words, simplify, the structure was something like this, no? I think. Cantilever, this, and I think this, no? Okay. What is the load at the end? What should be the load at the end? 0, so that's what it is. Okay. I remember we did the variation, I think was going from whatever, one value here. We got to a value, I know we had another one here, no, I think. It was going to one value here, then it was going to another value here, and then it was going to 0. Everything in tension. That's what we derived yesterday. Okay, so now if we do the math over here, FKH at 200 should be equal to what? If we didn't do any mistake, FKH, this gives you equal to, sorry, 257. Basically, it's the 2,257 minus the 2,000, no? It will be 2,000. So 257.1 newtons. And what should be F at point K? So Fk will be FKH, oops, sorry, will be FKH at 300. And it will be correct. What should be the load at the end? 0, no? Okay. All right, so basically, if I do the plot of the load over the actual loads over the stiffener DKH, yeah, sorry, I keep. Let me know when you're copying this, and I move to the next page. I mean, if you don't read it, don't be shy to ask me, okay? I don't know, you know, I'm writing normal, but I don't know if you can see it on the screen or not. I mean, this is like you did in statics in order to find, but instead of finding the shear bending moment, what we're trying to find out here is the value of the axial force, no? Along the member. All right, so I'm going to put this on top. And basically, let me kind of redo the figure here, since it's on the previous page. We have D, K, H. We have Q1 over here. Q2 over here. 60 F1 equal to 4,000. And basically, what we have derived is what? Is that at point D is 0, here is equal to 2,257.1. Then, because of the 2,000, we go down here to 257.1, and then it goes to 0.
So, Professor, can you do the figures?
Oh, sorry, yes. I was trying to do too much. Okay, are you done with this over here? So basically, that will be the distribution, no? On that different. We started here, FD equal to 0. We had this equation will be the 11.3s. This will be 11.3s, right? And this one will be the long one. But since we are here and do this one, and I think I just told you that, oops, okay, do I have to open this? I think maybe I can go here. I think we're just talking about this, saying that if you wanted this the fuselage frame, you could open in this. Basically, that should be kind of the same problem. I did it a while ago, okay? So it's whenever I did it. So you see, I let you know how to do it. Blah, 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 blah. Probably you can start looking at the deformation, but so here probably you see you can start reading. Maybe you cannot see. Maybe if I can magnify it here. But this should, maybe you cannot read, but probably you can be able to read. This should give you here the value for the shear. Okay, so you can go and check. And probably I also did, remember this would be the load on the top flange. No? It was positive. This will give you the one at the bottom. You don't see it here, but you see it goes here. Tension, then it is compression, then it switches over here to tension into that element, no? And it has the same one for all these ones over here. Okay, so let's say I probably did element per element. Yeah, so this will be just the top. Then this will be just the bottom. You see here the switch. Okay. Then I don't know if I did the tip, no tip. Let's say whatever. Looks like you see I do here different ones, no? Different stiffness. So what I want to say is that if you spend the time to look at this video and do it, you can go and check the answers for this problem and also the answers of the problem for the assignment, but it's not required. Okay? You can do it if you want. I think it will be good practice. Okay, so you see with the final element, you can check everything. Okay, I don't know what I'm doing. Okay, I've done that a long time ago. But what I want to say is that you can come and check it. All right, so now we're going to look at another stiffener. Now look at the stiffener BF. So let's see, stiffener BF will do more or less of the same. I guess that's the one that is the closest to the wall. Yeah, we have here BF. At point F, we had a force of 5,000. So let's see, what should be BF equal to? What should be BF equal to? What should be the load at point F? 5,000, no? Okay. And all right. So again, in this time, let's see on the figure we have on this side, left-hand side is Q4. This side you have Q3. And the whole thing is 300. So again, in order to find the internal force, we make a cut anywhere. If I make the cut, this is going to look like what? Kind of as before. We're going to have here Q4. We're gonna have here Q3. We're gonna have over here, I got this one F BF. Again, they select here to be S, starting from the top, same as before. And again, I have here on this page, I don't know if it's or not, I mean, I guess it's correct, that Q3 we find out to be equal to 6.67, Q4 equal to 23.33. So if we apply the forces along the stiffener, this will give us what? It will be Q3 times S, no, positive, minus Q4 times S plus FDF equal to 0. So this will give you FBF will be equal to what? Q4 minus Q3 times S, which I think this is equal to FBF, will be give you to 16.
Slide up.
Yeah, 16.667 S. I don't remember having to do this yesterday all the time. Okay. That's fine. I mean, I don't mind doing it.
Maybe if you move the camera forward a little.
Oh, yeah, it's true. Maybe that's what it is. Yeah, it doesn't change.
If you tip it a little, tip it at the top.
To move it a bit up, you said?
Yeah. Like
Whatever works, you know? Yeah, I don't think it's changing much, huh? If I can. And it's already zoom out. So, I mean, whatever, we work with it, okay? So now, again, so this will be all the way to the end. So if this is correct, what should be the FBF? If you want, you can take your calculator and check. But what should be this? If everything is correct.
5,000.
Yeah, should be equal to 5,000, no? So if we do our figure over here, if we do the same diagram as over there, 1, 2, 3, 4, 5, 1, 2, okay, one more. So here we have the 5,000. Here we have the Q4. Here we have the Q3. The distribution for this one. I'll move it up again. Yeah, no, sorry for that, guys, but it's like, sorry for that. Let me know. So basically what happens is that we start from 0. It will be in tension because the values we're getting is positive. So the whole member will be in tension, and this will be going to 5,000.
Just like 5 snap going on.
Yeah, sorry for that. Yeah. Okay, so okay, I think the procedure is clear. So I'm going to speed up a little bit. So 1, 2, 3. All right, so let me move it all up. So following. a similar procedure. All right, this one is to go too far. We can look at the stiffener. CG. And the stiffener. JK. So here we have C, J, G. So this one I think is goes from is in compression. So this will be compression to negative 923.1 at point G, and then it goes to 0. Compression. And the last one, this one I think is, so it will be here. I guess this one will be tension. You go from 0 to 3,464.1. Okay, so this will be the end of the problem. Okay, again, I will highly encourage you to go and check and do the FinMap Nastran problem, no? That you fully understand. Again, since you don't have computers in class that we cannot do together in class, I don't make it required, okay? All right, so one thing over here, I'm gonna put some comments, some notes. So, and this is generally something that you always ask me, or so shear flow. Approximation in a let's say a wind box. Fuselage frame. Okay, so let's say generally when it's easy, you do this. That's the one we just did. Okay, so let's say there's a force over here, V. And let's say the depth of our wind box or panel is H. So what would be a good estimation for the shear? Okay, Johnny, the shear would be what? If you think about it, what is the units of the shear? Is force per unit length, no? So Johnny, you tell me what is a good, I mean, and this is what almost everybody does it all the time, so it's not you. But I know that's what they teach you, and it's fine. So Johnny, what would be the shear flow over here would be the value of the force divided by the distance that it goes is over H, no? Okay, the one this is shear flow. So now the question is, how to determine shear flow for a curvilinear cross section. So basically, I do kind of a similar figure. Yes, sorry. I do kind of a similar figure here. And do this. So the reason why I added this stuff, I think, is last time is because somebody told me that for them, the shear flow going from here to here, going to this member, is the same as going from here to here. Can be one approximation, but it's not really true, no? Okay, so what I'm going to do next is how to find the shear flow for something that is curvilinear. And I'm pretty sure you have done it as well in structures 1. One, 3, 4. Okay, so let's put here shear flow in curvilinear member. This might be a review, but like I told you, I don't expect anything that we do in class is we should be able to use the classes to do any assignment, no? Without having to go to a book or previous classes. Okay, so let's look at a curvilinear. So let's look at a general curvilinear member. Let's say I do it this way. Let's say this goes from here to here. All right, so say it would be the center. And let's just say that we go from bottom to top. We could do it differently. Let's say we go 1 to 2. The reason is because I like generally to say that counterclockwise is positive, no? But it doesn't matter. So we look at what should be the shear flow between 1 and 2. Okay, so in order to do that, like we did before, we need to define a starting point from where to calculate. So let's say it will be S. We'll go from 1 to 2. The distance here, I'm going to call it P, but basically this would be the radius. And I make it here perpendicular. And then here will be something of an element. Let's say we need to find the area element. So let's call this one over here dA. Okay, and obviously something needs to create this. So let me say that I create a moment over here, put a moment over here. Let's call it M12. Okay, we could just call it that. Okay, so before, let's look over here. So what would be dA approximately would be equal to what? would be, can you approximate the area of a triangle? If this is very small, this would be almost like a triangle, no? So what is the area of the triangle? Would be what? P times ds, this little arch over here. Let me put this, maybe this would be ds over here. That little segment times P. And I take half because that would be the area of a triangle, no? Half the area of the rectangle. Again, this is not important. The only important is the final equation. Now here I can rewrite this. I can say from this equation that PDS equals to A. So here, because this is a differential, I can integrate this between 1 and 2. And this is what over here. So let's keep this expression over here. Let's call it I. Okay. Again, the division is not important. The important division is that you understand it, not that you fully remember. So now we're going to do summation of moments about point O equal to 0. And if you want, we can put counterclockwise positive. It's not going to change anything. So then what should be the moment? This one, I did it clockwise. So we're going to have minus M12. And now what will be the moment created by the shear flow on the curvilinear element? Would be. So would be Q12 times that's whole distance, no? Correct. So that should be what? If we're accurate, it should be what? This should be equal to ds between 1, 2. This should be the value of the force, no? Correct. And what would be all the time the arm for the moment? P, no? The radius. And this should be equal to 0. So if I rewrite this a little bit differently, I write this as minus M12 plus Q12. Now you see I replace this one. P is a variable. I just write this as PDS 12. What is this term over here? This term is equal to what? To A, we're going to have 2AQ12 equal to 0, or you're going to get that M12 equal to 2A Q12. Do you kind of remember that equation from Structures 1? I'm sure you have used it. Okay. Again, the division is not important, just that you understand it. Okay. So we'll be using this very soon. I don't know if in today's lecture or next one, because this semester I'm adding something. Okay. Which generally I wasn't covering because I don't think it's that important, but you know, to make it a bit different than other semesters. So let's move to that part. And this is actually because it's covered by Dr. Radosta. Okay, so what is the reason of the next section? Okay, if you look at an aircraft, to tell the truth, I'm sure there is some of them, but I think to give a percentage, more than 90% of all the panels are rectangular. No? Okay. But obviously, what happens if the panels are not perfectly rectangular? Let's say they are tapered, no? Then the shear flow within each one of the elements is not going to be the same, no? Okay, in other words, so let's see. Let's put over here. So let's say we finish this. So in an aircraft, let's say the vast majority of the panels are rectangular, so let's say this way, but what happens to the shear flow if the panels are tapered? So in other words, let's say the panel to be this way. Okay, so in this case, what was the assumption that we did? Is that, remember, we said that it will be up, down, right, and left. No, sorry for that. But it was, we could follow that notation. Here you see, since the edges, this one and this one are not parallel, this one and this one is not parallel, what's really going to happen with the shear, no? Okay. So I didn't used to cover that, but now I'm going to cover it. All right.
What updates are available?
Sorry.
There's something. There's a window open. If you
Oh. No. Obviously, not to everything. So, okay, so I should have, no? That gives you more. Okay. So taper. Shear panels. Okay, so let's start by just drawing one that would not be rectangular. So let me do this. And maybe this over here, like this. All right, so let's say this would be our panel now. Oh, this is going to be difficult. Okay, so let's say they cut over here. If I'm lucky. This will be Y. To the X. Let's call this one H long. So H sub S, L is for long. This one would be H sub S for short. This would be the theta T for top. And this would be theta B for bottom. So let me maybe write this top S for short, side, L for long side, B for bottom and capital T for top. Okay, what else do we need? So we're gonna need, so let's see. All right, so this will be, that distance will be X shorts. So this will be the location of the short panel. Okay, the vertical short panel will be at X. This will be now X long. And I don't know if we need this or not, but let's just say that this distance, let's call it L. Okay, I don't want to put too much on that figure, so I'm going to create another little figure. So let's say, and assume all shear flows are constant along the edges. So basically, the only thing I'm trying to say is very simple, is, let's see. So this is 1, 2. This way, what I'm trying to say is that the total value that would be going on the long side, this one will be constant. There will not be any variation. Same thing here for the short. So you see, this should be equivalent to, remember the sign convention that we did, up, down, right, and left for a rectangular panel. So this is the same thing, Q long, then this would be the Q top, and this should be the Q bottom, no? So this was the shear distribution for a rectangular panel, no? Okay, so now it will be constant, but because it's tapered, it's not the same thing. They might not be equal. All right, so what we're going to do over here, again, the deviation is not that important, but like in statics, what do we mean? I like to give you this stuff, but every class in structures, what are the 3 equations that you use all the time? It's only 3 equations. Other classes of structures are based on what? Newton's statics law, no? Newton's first law, summation of force equal to 0, summation of moment equal to 0, because this will give you all the value of the forces, which are vectors. But then you need to be able to relate what? All these forces to what you need to be able to relate them to what? To the material, no? What is the equation that relates materials and deformations? Hooke's law. Sigma equal to E epsilon, no? Strength. That's the equation now, because stresses is what? Forces over area. Strain is what? Deformation, no? Elongation of initial length, and E is the material. So if you combine those 3 equations, you know structures. That's what you do in structures. What do you do in fluids or aerodynamics? You only combine 3 equations again. Summation of forces, but this time is summation of forces equals to MA because it's moving the fluid now. Summation of moments equals to I alpha. And then what is that magic equation that relates to forces, the forces to the fluid? Don't you have one called tau equal to the viscosity times the velocity gradients? Okay, that's what you do. You relate those three equations, use those three equations in every single class of fluids or aerodynamics. All right, very good. Let's do this. Okay. So again, so we're going to use what? The static equation. So we're going to do summation of forces here along the x. This is not moving, so it's equal to 0. So this is going to give us what? So let's see. Let's start by Q sub t. So we start Q sub t. So if you look at the angles, okay, let me write it down and then we check it. What would be the x component? It would be L cosine theta t will be this whole length over here. Times cosine theta t minus Q sub b. So bottom of L over cosine theta bottom times cosine theta bottom equal to 0. So this becomes, you see, this cancels, and cancels. So it becomes very easy. This means that Q top times L minus Q bottom times L equal to 0. So from this equation, we can determine that Q top will be equal to Q bottom. And just to use a different notation, we're going to call this one Q hat. Okay, so that's good. At least this one and this one are equal. Okay. All right, now we do the same thing. Maybe let me go to the next page. So continuous. Next page. We're going to do the same thing, but summation of forces on the y. Again, the derivation is not that important. It's just at the end that you write down the equation. All right, page 6. Now we do summation of forces on the y equal to 0, which is going to give us minus Q sub s H sub s. So if you look at the figure, what is that? Is on the y direction is H sub s, then Q sub s would be the value of the force now. Okay. We do the same thing on the other side, plus Q long, so Q sub L, H long. And now we need to see what will be the y component of the Q top and Q bottom. So we get kind of similar. We get, this will be plus, okay, Q top of L cos theta t sine theta t minus Q low L cosine theta bottom sine theta bottom equal to 0. But recall the notation that we just say that Q top, Q low, we use the different notation. This is Q hat. All right, so basically, we do some basic algebra over here. We get that Q sub L, H sub L will be equal to Q sub S, H sub S, plus Q hat L tangent theta bottom minus Q hat L tangent theta top. Okay, this will give us that Q sub L is equal to Q sub S, H sub S divided by H sub L minus Q hat of L tangent theta top minus L tangent theta bottom. Okay, again, don't worry that much about the division. And all this stuff over here is actually equal to HL minus H short divided by H long. So basically this will give you that Q long will be equal to Q short H sub S over H sub L minus Q hat. Again, divisions are not important. I'll tell you what is the equation you can write down on a piece of paper, but you can use them. Minus H sub S over H sub L. And this will be equation A. Okay, next we're going to use the other equation we can use in statics, which would be summation of moments about point A, counterclockwise positive. So where is point A? So point A would be this is our final, this would be point A, okay? This one over here. And this should give, so you will get Q sub L, H sub L times L minus Q hat, open bracket. Oops, sorry. Can I do that? Yeah, it's fine. I can do that. The L over cosine theta top times cosine theta top H sub S equal to 0, because what would be the moment created by the two shear flows going from this one and this one? It's going through point A, so they will be 0, no? Correct? So we should only have this one over here and this one, no? Creating moments, all right? That's basically what we're doing. So from here, you're gonna get the equation that Q hat is equal to QL, because this will cancel. So Q hat will be QL over HL divided by H sub S. This will be our equation B. Next, we say substituting. Can you read? Yeah. Substituting B into A so this will give you Q sub L will be equal to Q sub S H sub short H sub long minus Q sub L H sub L H sub short HL minus HS divided by HL equal to 0. This gives you at the end that Q sub L equal to Q sub short H sub S over H sub L squared. Almost there. Let's call that equation C. One more equation, that's it. All right. Next, we're gonna write down. Yeah, sorry. Again, the derivation, just good that you follow it, but I'm not gonna ask you any derivation, okay? Done? So finally, we're gonna do substituting. C into equation B. That means that we're gonna have Q hat equal to QL H sub L over H sub S. This will give you equal Q sub S H sub S over H sub L square H sub L over H sub S. So this will give you that Q hat equal to Q short H sub S over H sub L. Okay, so we have done all the derivation, but now, okay. So let's say in summary, if Q short is considered as the unknown shear, what are we gonna have? So let's see if I can make it a bit bigger. Hopefully I'm not gonna mess it up. So we'll be 4 now. 4. Yeah. Okay, so let's say that the Q short, I do the same thing as before. So Q short is the unknown that we want. Okay, so if you look at the derivation, Q long is equal to what? Should be equal to equation C. What is Q long in function of QS? Is equation C, which should be, you see, Q short times short height divided by long height. You take the square. And then this one at the top, over here, and over here. This one is equal to Q hat. And we say that the Q hat was equal, and the Q hat was equal to what? We have it right here, no? Is this expression here is equal to Q short H sub S over H sub L. So basically, if there's one thing you need to write down on a piece of paper or something is this over here, the deviation is not that important. Like I told you, I didn't use to cover this. I think it's a lot of deviation for not much, no? I mean, any question why we did all this stuff? The important thing really is this one, no? Okay, so let's just do one example. And then we'll see what we do. So this would be page number 7. Okay, so example. Let's say I'm going to do here the figure of a non-rectangular panel. So 1, 2, 3. Here I put 2. Okay, so here we go. Here we go. Let's say this one, they do this. Oh, maybe we finish with this. All right, and let's say there's a force over here applied of 5,000 newtons. And let's call each one of these edges 1, 2, 3, 4. If you ask me, I think somebody is not here. No. But this is one example that I took from, I think, Radostas class notes, okay? If you ask me. So remember, this one is each member, but remember all this stuff, there's skins or panels, no? On every single thing. Okay, so we have some measurements over here. So let's say the length over here. Between 1 and 4, this will be 1 meter. The height of the short panel is 0.45, and the one over here this is what? 0.60, okay? And everything will be in share. So the question over here is to determine the shear flows in the tapered panel. Okay, so basically this is straightforward. So maybe for simplicity, let's just see which one represent what. So this would be 3, 2, All right. So this side would be what? Remember, we take that one as a reference to be the short. This one here would be the long. Then this one here will be the Q top, but we said that the Q top was equal to what? Q hat, and that this one over here is equal to the Q bottom, which is also Q hat. Okay, what are the other quantities that we need? If we look at the page we just derived over here, we need to know the Q hat and what else? The H sub S and H sub L, no? So over here, what would be H sub S would be equal to what? 0.45 meters. H sub long would be equal to 0.6, okay? Okay. But we don't have L, no? Do we have L on one of the equations? I think we don't need it. All right. So again, I mean, I don't think I'm going to do it, but I mean, if you want, maybe let's do it for the first time. So. Okay, so if you want, since we use this notation, I'm sure you know how to go from one to the other, but. So let's say, so then from the figure, I don't think this is necessary, but okay, since we have time, yeah, we have time. Q12 will be Q long, Q23 will be equal to Q hat. Q34 will be our Q short. And Q41, or maybe, well, let me change something. 14 will be Q sub hat. And let's say this one is correct. And here, let's say instead of Q23, let's do Q32. So at least we go on the correct direction for the sign. Q32 will be Q hat. Okay, so in order to find all these ones, Q12, Q23, Q14 for one, what is the only one we need to solve for? Q short, no? What can we do in order to solve for Q short? So for Q34 equal Q short. What is going to be the value? What is the value of the force in that member? $1,000. And what is the height? Okay, so basically that's what we need to do, no? Okay, but mathematically we can say summation, if you want, summation of y equal to 0 along member three, 4 gives what? What do we get? We will get Q sub S times 0.45 minus 5,000 equal to 0, which means that Q short will be equal to, let's say, 5,000 divided by 0.45, which I have no idea. So QS I think I have it here. Yeah, QS will be 11,110 newtons per meter. Okay, so now what do we need to do in order to find the other ones? We need to use these relations, no? Okay, so here we go. So using the relations in page, whatever, in page 7, okay? Or whatever is your page, okay? I changed the number in recent class, but with basically these equations here. We're gonna get that Q long, which Q long is what? Let's see, what did we say was Q long? Is Q, yeah, but is Q long is Q12, no? Yeah, Q12. And now the definition that we're using is Q short, correct? Times H short over H long square. So I'm doing the first one. So this is 11,110 times 0.45 divided by 0.60 square, which will give you that Q12 is equal to 624.375 newtons per meter. Then we say that Q bottom is actually what for us is Q32, correct? And the equation for that one is Q sub S H sub S over H sub L. So again, 11,110 0.45 divided by 0.60 equal to 832.5 newtons per meter. And finally, okay, we know that Q top is equal to Q bottom, and this should be which one? Q 14, no? So this one is equal to 832.5 newtons per meter. Okay, so let's summarize the result on a figure. So let's see, what did I do the figure here? 1, 2, 3, 1, 2. So 1, 2, 3, 1, 2. So basically, what do we have? We have over here Q short equal to 11,110. Q top, which is whatever, Q 14, no. Yeah, Q14. Q top equal to 832.5. All right, this one is Q, and you put the number in, might be a lot easier than 1, 2, 3, 4. So Q32 equal Q bottom equal to 832.5. And finally, Q12 equal to Q12 equal to Q long. And this is equal to what? 624.375. Okay, so I think on the assignment, I didn't put one of the taper because I was using one of the old assignments. So I'm gonna add this problem on the assignment, okay? One of these problems for the assignment. And that's it for today, no?